Space is vast. It stretches out in all directions, seemingly infinite and filled with countless wonders. From the smallest particles to the largest galaxies, the universe is a treasure trove of mysteries waiting to be explored. It's filled with amazing things. Galaxies, nebulae, black holes and more. Each of these celestial objects holds secrets about the nature of our universe and the laws that govern it. One of the most fascinating is stars. These luminous spheres of plasma are not just beautiful to look at. They are also the powerhouses of the universe, driving many of the processes that shape the cosmos. They are giant balls of hot gas. Composed primarily of hydrogen and helium, stars undergo nuclear fusion in their cores, converting these elements into heavier ones and releasing vast amounts of energy in the process. They light up the universe. The light from stars travels across the vast distances of space, illuminating everything in its path and allowing us to see the beauty of the cosmos. This heat inside stars is called thermal energy. It is the result of the intense nuclear reactions taking place in the star's core, where temperatures can reach millions of degrees. Thermal energy is all around us. On Earth we experience it as heat, whether it's the warmth of the sun on our skin or the heat from a fire. It's a fundamental aspect of our daily lives. It determines how hot or cold something is. The amount of thermal energy an object has affects its temperature, which in turn influences how we interact with it. It's the energy of moving atoms and molecules. At a microscopic level, thermal energy is the kinetic energy of particles moving and vibrating. The more they move, the more energy they have. The faster they move, the hotter something is. This is why boiling water is hot. The molecules are moving rapidly, colliding with each other and transferring energy. In space, thermal energy plays a crucial role. It drives the formation of stars and planets, influences the behavior of galaxies, and even affects the evolution of the universe itself. It governs the birth, life, and death of stars. From the initial collapse of a gas cloud to the explosive death of a supernova, thermal energy is a key player in the life cycle of stars. It influences the formation of planets. The heat from a young star can affect the materials in a protoplanetary disk, leading to the formation of planets and other celestial bodies. Without thermal energy, the universe would be a very different place. There would be no stars, no planets, and no life as we know it. The cosmos would be a cold, dark, and lifeless void. Imagine a universe without the warmth of stars. It would be a place of perpetual darkness where nothing could grow or thrive. It would be a dark and lifeless void. The absence of thermal energy would mean the absence of the processes that drive the universe, leaving it static and unchanging. Thermal energy is the engine that drives the cosmos. It powers the stars, fuels the formation of planets, and influences the behavior of galaxies. It is essential for the existence of everything we know. From the smallest microbe to the largest galaxy, thermal energy is a fundamental force that shapes the universe and makes life possible. Stars might seem like simple points of light. When we gaze up at the night sky, it's easy to think of stars as mere decorations, tiny dots scattered across the vast canvas of space. But these seemingly simple points of light are far more complex and fascinating than they appear. But they are complex and powerful objects. Each star is a massive, glowing sphere of hot gas, primarily hydrogen and helium, held together by its own gravity. They are the engines of the universe, driving the creation of elements and the evolution of galaxies. At their core, a process called nuclear fusion takes place. This is where the magic happens. Deep within the heart of a star, temperatures soar to millions of degrees, and pressures are unimaginably high. Under these extreme conditions, hydrogen atoms collide and fuse together to form helium. This process is what makes stars shine. The fusion of hydrogen into helium releases a tremendous amount of energy in the form of light and heat. This energy travels from the core to the surface of the star, eventually radiating out into space, making the star visible to us. Nuclear fusion is like a cosmic recipe. It's a delicate balance of forces and reactions. The star's gravity pulls everything inward, while the energy from fusion pushes outward. This balance keeps the star stable for millions or even billions of years. It takes lightweight atoms like hydrogen and fuses them together. The process starts with protons, the positively charged particles in the nucleus of hydrogen atoms. When these protons collide with enough force, they stick together, overcoming their natural repulsion. The result is a heavier atom, helium. This fusion process not only creates helium but also releases energy because the mass of the resulting helium nucleus is slightly less than the total mass of the original hydrogen nuclei. This missing mass is converted into energy, according to Einstein's famous equation, E at mc squared. This process releases an incredible amount of energy. Just a small amount of mass can produce a vast amount of energy. This is the same principle that powers our sun and all the stars in the universe. Imagine holding a tiny grain of sand. It's almost weightless in your hand, seemingly insignificant. But in the realm of nuclear fusion, even something as small as a grain of sand can have profound implications. Now imagine that tiny grain releasing the energy of 1,000,000 bombs. The energy released from nuclear fusion is so immense that it can be compared to the detonation of millions of hydrogen bombs. This is the power harnessed by stars, fueling their brilliance and longevity. That's the power of nuclear fusion. It's a process that not only powers the stars, but also has the potential to revolutionize our own energy systems here on Earth if we can learn to harness it safely and efficiently. This energy is what heats up the star. The intense heat generated by nuclear fusion causes the star's outer layers to glow, creating the light that we see from Earth. This heat also drives the star's internal processes, influencing its life cycle and evolution. It's what makes it shine so brightly. The light from a star can travel across vast distances, reaching us here on Earth and allowing us to study these incredible celestial objects. Without this light, the universe would be a much darker place. Without nuclear fusion, stars would simply be cold, dark clouds of gas. They would lack the energy needed to shine, and the universe as we know it would be a very different place. Nuclear fusion is the key to the stars' brilliance and the driving force behind their existence. The core of a star is an extreme environment. Temperatures reach millions of degrees, the pressure is immense. These conditions are essential for nuclear fusion to occur. Think about striking a match. You need enough heat and pressure to ignite the match head. It's similar in a star's core. Extreme heat and pressure are needed to start and sustain nuclear fusion. The intense heat at the core creates outward pressure. This outward push prevents the star from collapsing under its own gravity. It's a delicate balance between gravity and energy. This battle between gravity and energy is crucial. It determines the star's size, temperature, and ultimately, its fate. Section 4. Energy's journey from core to cosmos. The energy produced in the core doesn't just stay there. It embarks on a journey outward, traveling through the star's layers. This journey is what makes a star shine. One way energy travels is through radiation. Just like heat from a fire warms you, radiation carries energy from the core towards the surface. Another way is convection. Think of a pot of boiling water. Hot water rises, cooler water sinks. Similarly, hot plasma rises in a star carrying energy with it. This constant movement of energy is what keeps the star inflated and prevents it from collapsing. It's a dynamic process that ensures the star's stability. Section 5. Shining bright. How stars light up the universe. The brightness of a star is directly related to the amount of thermal energy it produces. Hotter stars are brighter. They emit more light and energy. The Hertzsprung-Russell diagram is a tool astronomers use. It charts a star's brightness against its temperature. This helps us understand a star's life cycle. Imagine a graph with bright stars at the top and dim stars at the bottom. Hot stars are on the left, cool stars on the right. Each dot on the graph represents a star. By studying this diagram, we learn how stars evolve. We can predict how their brightness and temperature will change over time. Section 6. A delicate balance. The life of a star. Stars exist in a state of equilibrium. This means forces within them are balanced. Gravity pulls inwards while thermal pressure pushes outwards. Think of a balloon. The air inside pushes outwards while the balloon's elasticity pulls inwards. This balance keeps the balloon inflated. A star is similar. This balance is called hydrostatic equilibrium. It's what keeps a star stable for millions or even billions of years. However, this balance can't last forever. As a star ages, it uses up its fuel. This is when the balance starts to shift. Section 7. Stellar evolution, the fate of stars. As a star ages, it runs out of hydrogen fuel in its core. Nuclear fusion, the process that powers the star, begins to slow down. This is a critical phase in the life of a star, marking the beginning of its transformation. The core contracts and heats up, while the outer layers expand. This change in the star's structure leads to a series of dramatic events that will determine its ultimate fate. The outward pressure, which has been counteracting gravity, decreases significantly. Gravity starts to win the battle, pulling the star's material inward. This gravitational collapse is a pivotal moment, leading to different outcomes based on the star's mass. The balance between pressure and gravity is delicate, and any shift can lead to a cascade of changes. What happens next depends on the star's mass. Stars come in a variety of sizes, from small red dwarfs to massive blue giants. The mass of a star determines its temperature, luminosity, and lifespan. Smaller stars have a more prolonged and less violent end, while massive stars experience a more explosive finale. Smaller stars, like our Sun, will expand and become red giants. This phase is characterized by the star's outer layers swelling up and cooling down, giving it a reddish appearance. The core continues to contract and heat up, eventually leading to the fusion of helium into heavier elements. This process can last for millions of years, during which the star sheds its outer layers into space. They eventually cool down and shrink into white dwarfs. A white dwarf is the remnant core of a star, no longer undergoing fusion reactions. It is incredibly dense, with a mass comparable to the Sun, but a volume similar to Earth. Over billions of years it will continue to cool and fade away, becoming a cold, dark object known as a black dwarf. Massive stars have a more dramatic fate. These stars, much larger than our Sun, go through a series of rapid and violent changes. Their cores become hot enough to fuse heavier elements, leading to the formation of an iron core. Once the core is primarily iron, fusion stops, and the star can no longer support itself against gravity. They explode as supernovae, the most powerful explosions in the universe. A supernova releases an enormous amount of energy, outshining entire galaxies for a brief period. The explosion disperses the star's material into space, creating shock waves that can trigger the formation of new stars. These explosions can outshine entire galaxies. The light from a supernova can be seen across vast distances, making them some of the most spectacular events in the cosmos. The energy released in a supernova is so immense that it can briefly rival the combined light of all the stars in a galaxy. The death of a star is not the end. The remnants of a supernova, known as supernova remnants, are rich in heavy elements. These remnants expand and cool, eventually mixing with the interstellar medium. This material can become the building blocks for new stars, planets, and even life. The material ejected into space during a supernova can form new stars and planets. Nebulae, the colorful clouds of gas and dust, are often the birthplaces of new stars. The cycle of stellar life and death is a continuous process, driving the evolution of galaxies and the universe as a whole. It's a cycle of stellar life and death that continues to shape the universe. From the birth of a star in a nebula, to its death as a white dwarf or supernova, each stage contributes to the cosmic tapestry. The fate of stars is a testament to the dynamic and ever-changing nature of the universe.